All right, guys, let's look at another example of an operational amplifier. And once again, we're assuming this is in its ideal operating conditions. We have a negative feedback situation where some of the signal gets fed back into the inverting input. So we should be good. That tells me that whatever my voltage is here let's don't call that V1. Let's call that V3. We'll see why in a minute. And this will be V2. And they're the same. So V3 is attached to ground, so we have 0 volts at the non-inverting input, so we must have 0 volts here. So V3 is equal to V2. That's a 2 right there. I know, in case you can't read it, is 0 volts. Okay, now this is not a standard inverting or non-inverting input. We have some sort of a mess out here we need to simplify. The first thing I notice is we have a current supply in parallel with a resistor. So I'm going to take everything to the left there, call that A and B. And I'm going to replace this with its Thevenin's equivalent. I'm going to convert it from a parallel current source to a series voltage source. And I've gone off and done that. Boy, that was quick. And when I get finished, that looks like this. So there's A and there's B. All right, so it's a little bit simpler, but we still have all of this stuff up in here. We don't just have one resistor coming in. So what are we going to do with that? Well, we do know how to do Kirchhoff's current laws at different nodes, doing a nodal analysis. Everybody loves nodal analysis, so let's call this V1 at this point. We'll call this V2 at this point. And here we have V out. Now notice V out is connected this right. So this is V out. All right, so let's do a Kirchhoff's current law at this node and then another one at this node, and that'll probably get us what we want. Okay, so there's our plan. Hopefully that'll give us V out at node 1. If I do a Kirchhoff's current law at this, the current in should equal the currents out. Okay, so current in is 10 minus V1 over 5K. Voltage drop divided by the resistance. The currents out, we have this one up through the 10K and the one straight across through the 20K. So we have V1 minus V out all over that 10K resistor plus V1 minus V2. Now V2 we know is 0 volts, okay? We have 0 volts here, so it'd be V1 minus 0, and that's my V2, all over 20K. Now if I were to, that's a mess. We'll come through and we'll multiply everything by 20K, our smallest common denominator. What do we end up with? 40 minus 5 V1 is equal to V1. Okay, 2V1 minus 2V0 plus V1, there we go. That looks good. And rearranging a little bit, what do we get? 7V1 minus 2V0 is equal to 40. There we go. There we have one equation and two unknowns. You guys can guess where this is going to head. All right, now let's look at my nodal analysis Kirchhoff's current law for node 2. At node 2, we have V1 minus 0 over 20K. And so that's the current in here. The current up that way is 0 minus V out. So you know it's a 0, 0 minus V out over 10K. Do a little algebra to that, and I can isolate it down to V1 plus 2V out. There you go, let me erase that. V1 plus 2V out equals 0. Now I'm skipping the algebra steps here. I did that off on the side. Who wants to watch someone do algebra? That's boring. Okay, I'll let you guys do that. So here we have two equations, two unknowns, solving for V out. And if you haven't figured out yet how to get your calculator to solve two equations and two unknowns, you really should do that. You're going to do that a whole lot in the next couple of years. So right off the bat, figure out how to make your calculator solve systems of equations. This gives me a V out of minus 2.5 volts. There we go. So that's what we want to do there. Lovely, lovely. Isn't that great? Brings tears to your eyes, doesn't it? All right, let's look at one more here. And then we'll give you a break. All right, here's another guy. All right, so let's see what we can do with that. Let's notice first off that if I have 0.4 volts here, that means that right there I have 0.4 volts. This does have a negative feedback loop, so it's probably in the linear range. So that means I have 0.4 volts right here, which means I have 0.4 volts right there. Hey, now all I need to do is a Kirchhoff's current law around here, and I can find V out, because V out is right here, but that means V out is right there. And I know my voltage here. Oops, I forgot my ground symbol. My voltage right here is ground. So current into this node equals current out of this node. And how much current is going into the op amp? You guys know that? It's 0. It's an ideal op amp, 0 amps. Of course, you know it's not actually 0. It's micro amps, but that's small enough. It's going to work for us. Okay, so the current into this is going to be this voltage minus that voltage over this resistance. It will be, let's see, Kirchhoff's current law at this node, 0 minus 0.4 volts over 10K is equal to 0.4 minus V out over 50K. All right, look at that. One equation, one unknown. Do a little bit of algebra, and you can come up with V out is 2.4 volts. That's a comma. Solve. I won't make you watch me do algebra, because really, who wants to watch algebra? All right, there we go. My output's 2.4 volts. Of course, we also want the current output. So that's the current through this 20K ohm resistor. We know the voltage drop across it is 2.4 volts. We know the resistance. So the current out is going to be 2.4 volts over 20K ohms. As it turns out, that is 0.12 milliamps. Or you could write that as 120 microamps. Either one of those would be correct. All right, there we go.